recording. Okay, cool. You guys can see me?
Yes.
Yes.
All right, let me go and get my markers out. But did you guys have particular questions for homework 11? I know there were a lot of counter questions and high-level code stuff.
I think my main question is like making sure that for, I think it was like the question number 4 or something with the digitally controlled oscillator with the multiplier, like making sure that I'm choosing an acceptable P and N, like the bit and then the P multiplier.
Right.
Just like, cause like, I don't know, it's kind of like arbitrarily just like picking like, oh, N equals 16, P equals 1,311. And it was getting me close to like the hertz, but I don't know if like I can just choose whatever I want. So
you can arbitrarily pick, though I would recommend just to be as efficient as possible. For question number 4, for example, you're already using a 35-bit counter, so just use the 35th bit, that most significant bit, and then choose your M such that when you multiply, you get 1 megahertz. Or in the case of question number 5, use the 33rd or 32nd bit, and then choose your multiplier such that when you multiply, you get 1 hertz. So just use the most significant bit. You don't necessarily have to, but since you already have that big of a counter, you might as well.
Oh, okay. Yeah, I definitely wasn't doing that, so that's probably helpful.
Yeah. Any other questions?
So just to make sure I'm doing it right then, so like my F out, I think, hold on, let me see which number this was. Yeah, so like for number 4,
Yeah.
so I was using the equation F out, like frequency out equals frequency clock times P over 2 to the N.
Okay.
And then, yeah, I had like 1 megahertz, and then I moved the 50 megahertz over. So I basically had like 0.02 hertz equals P over 2 to the N. And that's where I would put N equals 35, you said, because we already have a 35-bit counter. Or is it a 35?
That's correct. But just so you know, typically when you write this equation, you actually write it like this. Plus 1. And the reason for that is because for a 35-bit counter, the 35th bit, the topmost bit, is actually bit 34. And so then you do 34 plus 1. So if when you plugged it in, you did 2 to the 35, that's fine.
Okay.
Just keep in mind this is the typical one, where N is the current bit that we're pulling. So typically this is the way it's written, and then yeah, you would rearrange it, solve for P, get your P value, and then you would round P to the nearest whole number, just because you can't have a decimal portion.
Sorry, does it say 2 to the N plus 1?
Yes, that's right. Yep.
Okay. And then my other question about that was like, can I go over, like the 2 examples I want to say in the video, Dr. Harris had like just come slightly under the F.
That's fine. Yeah.
You can go over. Okay, cool.
Just as for more reasoning why it's N plus 1. I talked about this a little bit in one of the previous episodes. I think it was Fridays. I uploaded those all today, so if you guys want to look at the recordings, you can. But if you have a clock signal, and then you're looking at the least significant bit of whatever your counter is, for every 2 clock cycles, this guy changes. Has 1 cycle. So you have something like this. And so for the bottom bit, for bit 0, i.e. n equals 0, so that's the bit we're choosing. We have that whatever our period was before, or sorry, whatever our frequency was before, the frequency of this guy is half of that. And so that's why we write the n plus 1 up at the top, because this is the case where n equals 0. And if you plug in n equals 0 here, then you get 2 to the first power, which is dividing by 2. If we did it just 2 to the n, then this would be frequency of the clock divided by 2 to the 0. 2 to the 0 is 1, which would imply that this and this are the same speed, but they're not. So that's typically why we put n plus 1 here.
Right, because like I was thinking of it as like n was the number of bits, not like the position of the bit, I guess.
And
So-
that can, that'll work too. Yeah, absolutely. It's just going to be, well, yeah, that'll work. It's just typically that's not the way you'll see it written.
Oh, okay. I do want to like do it typically.
It doesn't really matter that much. as long as you get the right answer from it and you understand it, that's the most important part. And then yeah, select a p-value, round the, well, p or I'm going to call M for multiplier. It doesn't really matter too much.
And then,
Yep.
oh, sorry.
No, you can go.
I just wanted to confirm. So then, my sketch of the schematic basically looks exactly like my regular bit counter, except my bits are now, whatever, it was like 35 or something. And then instead of the adder adding 1, it would add whatever my p value is.
Yeah, that's about it.
Oh, okay. Okay, then I think I'm good. Sorry, Good Noodle. Sorry for like monopolizing the last 10 minutes. Just
No,
want to
you're
make sure
good.
I was doing it okay.
Yeah, that's pretty much it. It's just the same schematic you're used to. This is your n-bit counter, and this is the nth minus 1 bit, which is the topmost bit. That's your new clock. This is your original clock, and yeah, that's pretty much the whole schematic. All you really need to change is the m value and the n value here, and that's about it.
Thank you.
Yep. Good Noodle, did you have any questions for me? Or are you just absorbing the information from office hours?
I'm just absorbing the information, yeah.
Okay, sounds good. Alright, well, if you guys do have any other questions for me, let me know. I'm just gonna be, I have no idea. We'll see.
Okay, so I do have some questions, but I missed Thursday, so I'm not even sure if we went over this or not. So if we haven't, you can definitely tell me like we can wait, but I was like looking at some of the videos, and I was looking at like the multipliers and the dividers and the schematics and how the like crazy, I think it was in the example on the video, it was like I don't know, an 8-bit and an 8-bit or something.
Yep.
And there were like so many levels, and I was just trying to wrap my head around making that huge schematic. Like I get how we get there, but yeah, I don't know if it's like relevant or if we need to go through like how
I
that
mean,
actual.
we can talk about it, but you guys actually aren't going to talk about multipliers or dividers at all in class.
Oh,
So,
okay. Well then, I guess, yeah. Then we might not need to. I was just like going through some videos, so if we aren't going to go through it, I won't bore people, especially since somebody else
if you
just
guys
joined.
do go through it, let me know, because in the past, I don't think she's gone over it for 200. I think you do go over multipliers, dividers, and 300, but I don't think, at least not in Harris's 200, you'll do any of those. But if you do, let me know, and we can go over it. Yeah. Any other questions for me?
This is actually a question for Shanna. Is the video you're talking about part 8 of DDCA chapter 5, shifters, multipliers, and dividers?
Yeah, that's
Oh, okay.
actually the one I was watching. Yeah. Because like I didn't know what I had missed, and I think it's it was like the next after ALUs. And so I was like, oh, maybe this is what we went through on Thursday. But yeah, so I guess it's interesting though. Like the whole shift left, shift right is really interesting. But
Any other questions for me?
Isn't today your internship started?
Yeah, yeah. Today was my first day at the internship. I went in
Mhm.
at 8 this morning, and I was there till about 11. And it was just onboarding stuff, paperwork, and training videos and things. So not like too much to go on about, but it was a good day at work.
congratulations, that's so exciting.
Thank you. I'm gonna have to make an announcement to the class, but just so you guys know, since you're here anyways, I'm gonna have to move for Friday office hours. I think I'm gonna be moving those to in the afternoon. It'll probably be after 1. So anytime after 1 p.m., I'll probably throw a message in the Discord and have everyone and give everyone options like what time after 1 p.m. For Friday office hours. But the rest of the week, Monday through Thursday, is going to be unchanged.
Okay, sounds good.
Good Noodle, are you in lab? Are you in the second lab or the first? Because I think the second lab doesn't end until what, 1:30 or something? I think half of us are in that one, but
I think I'm in that one. Yeah.
so yeah, that would be awesome if we had Friday office hours like after 1.
Mhm.
I mean, I can check. I think it's 2:15 that your guys' lab ends, but I can check.
Oh, yeah, it's probably that late.
Yeah, 2:15.
It is 2:15.
Yes.
Okay, I'll probably list that as one of the options then, like 2:30. For Fridays. I think it depends on whether or not I come in to the university. Depends. I probably will because more than likely I'm going to be at my internship on Fridays working, and it's relatively close to here, so I can just drive to Novi and do it in person. But if it's too, yeah, I'll probably do that. I'll probably drive over here and do it in here, since I'm close by anyways. Yeah, I think I'll do that. I'll probably let Dr. Harris know, and then I'll send a message out to the Discord sometime after, probably later tonight or tomorrow.
So, does anybody else have questions? Because I actually had a question from today's lecture. But if somebody has questions about the homework, like, please go ahead before I ask.
I have no question.
Okay.
Go for it.
I didn't have any questions either.
Oh, okay. Awesome. So I think the slides haven't. I don't know. So I'm not referencing a slide. It's kind of like something she did on the board. But it had to do with. Just got lost when we were talking about some of the memory. Sorry, give me 1 second. I'm like trying to find it in my notes.
No, you're good.
Okay, it was the word addresses. And like once I wish I had a slide I could reference, Victor, because like you probably.
you
But
could,
I'm
if you look at the DDCA Chapter 5 like PDF, the lecture notes, it'll probably be after page 50 of the notes, or of the lecture slides. That's where all your RAM stuff is. Maybe even a little bit before that.
okay. Chapter 5, you said?
Yeah,
Wait.
Chapter 5.
Okay, I thought.
Or maybe even before that. It looks like memory starts at around page 40, or slide 40.
Okay. Oh, yes, I see. Okay, I'm gonna mute myself and try to find the slide
Yeah, go
that
for
I'm
it.
looking for.
Let's see. Someone else just came in. You got any questions for me? Or are you just here for the office hours? I don't think I'm able to hear you, actually. You unmuted, but I can't hear anything coming from your mic.
Oh, sorry, mine is push to talk. Can you hear me now?
Yeah, I can hear you.
Oh, okay. So, yeah, I'm not really sure what specifically. I guess it's just the divide by 2n for the counter, like that method for the counter, but with the multiplier, I'm not really sure how I would like picture a schematic for that.
Yeah, so the schematic is very similar to what it's very similar to what you've already had for counters in general. So I'm gonna go ahead and draw up the counter schematic.
Okay, so is it just like with a multiplexer in there as well, or?
Well, the nice thing is you actually don't need a multiplexer unless you want to change between different multiplier values. Here we just have a single multiplier value we're using, so we don't need a multiplexer, but I'll go ahead and show you what I mean. So this is an n-bit register, so say like 32 bits or whatever. And then whenever you have a counter, right, you have an adder in front of your register, which reads in two inputs. One of those is the current value in the register, the current count that we're at. And the other input is your multiplier value. So in general, if you want to figure out if you want to find a different frequency, so say you start with 50 megahertz like in your example problems and you want to get down to 1 hertz, you can do it with this equation. It'll look like like this, where m is the multiplier and n is the n is the number of bits, but more specifically, with this wire, with this bus, there are actually multiple wires in it. In this case, there's 32 different wires. And because of that, you can pick off any one of those wires and use it in this calculation. So n corresponds to which bit you're using. Could be bit 0, the least significant bit. Could be bit 1, all the way up to bit 31. So if you want to figure out what your value of m is for almost all the problems, you just take your counter and say it's 32 bits. The most precise value we can get is if we use the most significant bit. So bit 31 in this case. So when we have that most significant bit for n, and we want to solve for m, all we have to do is multiply the 2 to the n plus 1 over here, and divide the frequency of the clock over here, and we can solve for our multiplier, given that we know what our input frequency is, and we know what frequency we're targeting, we can calculate m. And then you would just round it to the nearest whole number. So that's pretty much the whole process for it. You just can plug it into that equation and solve for m.
Oh, okay. Yes, I do remember from the video. So basically, we're incrementing by the multiplier. Then I think that's what she said in the video.
Yeah, that's exactly right. Yeah, one way to think about it is every go. So every time you recalculate the value, or I guess every clock edge, every cycle, you add an extra m to whatever your number is. So you have a starting number, so I'll call it x. And then every single clock cycle, you're adding on whatever m was plus how many cycles you've gone. If you've gone 2 cycles, you've added on m twice. If you've gone 7 clock cycles, you've added on m 7 times. So in general, because you're adding m however many times, we define repeated addition as multiplication, and that's actually why it's called a multiplier, because you're repeatedly adding m. So that's why we call it the multiplier. And then for those homework problems, again, like I said, once you calculate m, it's probably not going to be a whole number. It'd be nice if it was, but I don't think it's going to be. So you round it to the nearest whole number, and then using that, that's your multiplier. You can plug it back into this equation and calculate the actual frequency you generate, because you can't have this multiplier m be like a decimal number. Say it's 10, but when you calculate it, it was like 10.1, but when you round it, it's 10. When you plug in 10 versus plugging in 10.1 here, you're going to get a different frequency. So for part of the problems, it asks you, well, hey, what's the actual frequency we get? Because your multiplier isn't exactly what you wanted. So you plug it in, and you can solve for the actual frequency. So if you were shooting for 1 megahertz, if you were shooting for, say, like 1 hertz, maybe you got 1.001 hertz, or maybe you got 0.999 hertz, or something like that. So there's going to be a little bit of an error there.
Oh yeah, I see. Thank you.
All right, any other questions for me? Okay, I'm going to go ahead and erase the counter off the board. If there are no other questions, Shauna, were you able to find the slide you were referring to?
No, it doesn't. Nothing in that section of the slides looks like what we had on the board.
Okay.
And I know Dr. Harris said something about uploading some additional slides today.
That's very possible. Maybe.
Maybe tomorrow I'll have something for you. But
Sounds good. Yeah, on my end, because I can see different stuff than you guys, but I still don't see any of the. Yeah, I don't see any like new slides that would have been posted today. But yeah, she probably will post them tomorrow, hopefully, or later tonight. Okay, well, whatever. Any other questions for me?
so I have a very random question, but like, what exactly? I haven't seen any like differences in what we've been doing in C versus C++. Like, are there a lot of differences down the line as we get more into it?
Not that you're going to be seeing in this class, not really. There are differences for sure, but most of the differences that you will care about in terms of just straight software coding, you're not going to really see in the examples you do in this class, because the examples are so, well, they're relatively simple, so you're not really getting into those minor nuances. Like, you're not going to be dynamically allocating memory for an array, for example. So you won't be able to see the difference between new in C++ and alloc or malloc in C. But again, you're not going to see those differences. So if you want, treat it like C++. That works too.
Thank you.
Yep. Any other questions for me? It'd be a shame if this office hours was basically over at 5:45. I'm not saying I'll leave, but I can only go on so long.
We were learning more about assembly code, and so when we're looking at when we compile C, the high level language, you compile it, we turn that into machine code, right?
You turn,
Machine.
So yeah, you turn the C code, the high level language, into assembly, and then the assembly gets turned into machine code.
Oh, I see. Okay.
Yeah,
So what form of assembly is C getting compiled into?
it just depends. Depends on
depend-
what,
oh, okay.
what your processor is. So, for example, if you're running on a RISC-V processor, it's going to compile down into RISC-V assembly. If you're running on a standard desktop setup, I think Intel and AMD both use x86, so it would compile down into x86 assembly. It really just depends on what the actual hardware you're using is and what machine code it can understand. So it varies from device to device. But for this class, it's going to be RISC-V that you guys will be compiling the C into. Any other questions for me?
Yeah, so this might be a stupid question, but I've never understood how, like, f equals -1 in hexadecimal. Am I just being, like, crazy?
I had
Do I
the
just think, like,
exact same question when I was taking
Okay.
200. Don't worry, it's fine. So let's pretend that you have a specific bit width. Say it was 16 bits. And here I actually have written out 16 bits, but in hexadecimal. If I was to actually write them out, each of these Fs would be a bunch of ones, right? So we have 16 ones in a row.
Oh, I see now. Okay. Yes. This
Two's
makes sense.
complement says flip all the bits so you get all zeros, and then you add 1, and that's going to be all zeros with a 1 at the end. So before we started, we had a number, whatever it was, and then when we negated that number, we got 1. So that must mean that the original number was -1. So just in general, if for whatever bit width you have, all the bits are filled with 1s, and you're interpreting it as a 2's complement number, that's always going to be -1. So if, for example, you had 18 bits, then this would be -1. Because here we have 16 ones from the 4 Fs, and then 2 extra ones from the 3. That's 18 bits of 1s, and if our total bit width is 18, then this represents -1. And that pattern continues. If you don't have every single bit in your bit width go to 1, then it's not going to be -1 anymore. But if you do fill them all up, it's always -1, yep.
Yeah, I think I didn't. It was like the 2's complement thing. I was like, how is this -1? Okay, thank you so much.
You're very welcome. Any other questions for me?
Maybe not. I'm not really sure if it's a question that you can answer, but I wasn't actually able to attend class today, so I was wondering, are we still covering the C code, or are we moving more into memory again?
I don't know. You can ask your classmates, though. I have no idea.
Okay.
Yeah, we did both. We did, like, the first half was the C code, and we went through, like, general functions and stuff, but then most of the class I feel like was memory, and like read from memory with the load word, and then write with the store word, and like how we like put things into the temp locations, or like S0, S1, S2. So that's what we went through.
Okay, perfect. Thank you.
Any other questions? Man, you guys must really be scrounging for those questions. Nah, it's all good. I'm trying to think about what, Shauna, what you were saying about the word addresses. Is it about like when you have memory and the alignment of the like words that you're storing in memory? Is it about that?
Yes, I believe. So what Dr. Harris wrote on the board was like a grid, and then
Oh, yeah.
she filled the grid with like 0, 1, 2, 3, all the way up to like A, B, C, D, E, F. And then I got lost when it was like the byte address of 0 equals 048C1014. I think I like really just got lost. But yes, that looks like something she drew.
So something like this is something you'd see in like a memory bank. And so each of these correspond to your addresses, and each of these columns correspond to a particular byte. So I'll go ahead and explain myself. Each of these little squares can hold 2 hexadecimal values. So what that means is it holds 8 bits, which is also called a byte. So 8 bits is the same as 1 byte, which is the same as 2 hexadecimal digits, which, as a fun fact, is also called a nibble. It's not quite a byte, just a nibble, which I think is pretty cute. So what you have here is a memory. Oops, that's wrong. Let me see. So what you have here is a memory, and each memory address corresponds to 1 byte. So it's what's called byte addressable. And literally what byte addressable means is that each byte within your memory can be addressed. Specifically, if I were to ask for the address of this box, I would say, okay, well, here in the row it's 0, 0, and then you add 0 to it. So this is address 0, 0. This address is 0, 1. The one next to it is 0, 2, and so on. So what the column corresponds to is what's called your byte offset. And then this, the labels along the left-hand side here, these correspond to your word offset. Okay, so with that in mind, what was your question in regards to this table?
So like, can I give you an example we did in class?
Yeah, sure.
And you can show me like where we came up with this. So we did SW, like store word, T2, which I understand, is the temporary repository
Temporary register, yeah.
register, excuse me, yeah. And then we wrote 0xc, and then in parentheses 0.
Oh,
So I understand 0xc, I believe, is the offset, and then 0 is our base, like, that we're offsetting, but
so
if you can
said,
show me
what was it like?
0xc, and then in parentheses 0 for the base address.
Like that?
It was actually the word 0,
Okay.
which
I was
Dr.
yes.
Harris, yeah, okay. I guess it corresponds to like S0, I believe.
So the reason why I was a bit confused when you said 0 there is because when you're doing store or loads, this value outside the parentheses always has to be an immediate. And when I say an immediate, I mean like just a number. Whereas the thing inside of the parentheses has to be a register. So there is a register called the 0 register. This is literally R0. So the word 0 corresponds to the 0 register. And the 0 register is special because in the RISC-V architecture, the 0 register isn't actually a register at all. It's just the number 0. So literally 32 bits of zeros, all tied to ground. And so this is a register here. And what this corresponds to is we're saying we're going to store T2, whatever T2 has. I'm going to say, let's say that T2 is this 32-bit hexadecimal value. And we're going to store that in memory at the location of this offset plus this number. So this total combination, this plus this, corresponds to where in memory we're going to store this value. So what this means is we're going to take hex C plus the number 0, and that's going to be our address. So we're going to say, okay, hex C is here, plus 0 is this row. So we're going to store this value in this spot in our memory. That's what that means.
Wait, sorry, we're storing it in the entire row of the memory? Each, because we said that was 32-bit, and each block is 8 bits?
Yeah,
Oh,
8 bits
okay.
or 2 hexadecimal digits. So we'd have A, B in one of them, C, D in one of them, 1, 2 in one of them, and 3, 4 in one of them. That's right.
Gotcha. Okay. And then I'm sorry, can you possibly zoom into, it's a little hard to read. Is it just 048C and then 1014 going upwards?
Yeah,
On the
0, 4, 8, C, 10, and then onwards would be 14 and so on.
Okay, got it. This makes sense. Thank you.
Let's see. There are 2 ways you could see it be stored, depending on if it's what's called little endian or big endian. So I don't know if you guys have gone over that in class. Have you guys gone over endianness in class yet?
I don't think so. That doesn't sound familiar.
Yeah, well, I don't think we have.
Okay, well, it's not a big deal. It's just the way you store it. So you can consider this to be, so this is the least significant bits of your number. And so you can choose to either store that at a higher byte offset or at a lower byte offset. So you could choose to store it one of 2 ways. You could store that number like this, or you can swap the byte order like this. And it may be a little weird because we're like, well, why would you store it this way? It doesn't really make sense. You just took each byte and swapped them around, and it's like, why would you do that? The main reason is because while this looks normal to us, this configuration looks normal to us, like visually, we need to remember that this is actually a smaller index in your memory. And so another intuition is, well, the smallest bit of our number, the least significant bit, should go in the lowest memory spot. So that's what we did here. The 34 I put in column 0, the lowest memory spot. The 1, 2, then in the next highest, the CD in the next highest, and the AB in the next highest. This is little versus big endianness. We have these 2 examples here. But you guys will get into that in class, and if you have questions after class, you can ask me.
So in the example we did earlier, instead of if replacing the word 0, could we replace it with like 0x4? And then would that shift everything? No. Okay.
So
2?
you can't replace this with an immediate. You can't replace this with a number. The thing inside this parentheses have to be a register. However, if you wanted to make this hex 04, what you could do is something like T1, and then you could say 0, and let's do hex 4. So I have this back. Imagine this is the first line that occurs, and this is the second. So we run this line, and basically what this does is it takes the 0 register, adds it with the immediate 4, and stores that in T1. And so now T1 holds the value hex 4. So what you can do then is you can say, I'm going to put T1. And so then this takes the offset hex C and adds it with whatever's currently stored in T1, and that's where it's going to store T2. So here, T1 holds the value of hex 4. Hex 4 plus hex C is hex 10. So this row is where T2 would be stored. That's how you would change this It has to be a register.
Okay, that makes sense now. Thank you. I think we did do something similar to that, but we used a -1 instead of like a hex address with our add I. So
yeah.
it's like add I T20 -1.
Yep.
Okay.
Let's see. Someone else just came into the Discord. You had questions on, was it 3 through 5 of the homework? Is that right?
Yes, sir.
Okay. So, just as a general recap, because we talked about it a little bit earlier, but the first thing that you want to think about for these problems is your schematic. So, actually, before I do anything, are you guys alright if I erase the memory stuff from the board?
Yes.
Yeah.
So again, when you're doing this counter thing and you're trying to find a new clock frequency, typically what you do is you consider just the regular counter circuit. So I'm going to draw that up on the board, and I'll do it in a different color. I'm feeling purple. So here we have our register, which is going to be remembering the value of our count. And it's going to be an n-bit register. And typically for a counter, you have an adder at the front of it. And this is the general circuit for any counter that you have. So you have your register here, which retains the memory of what the current value you're on. And then you have an adder, which basically adds that value with some number or multiplier. For your guys' introduction, this multiplier was actually normally 1, where you just add 1 every clock cycle. Though in general, you can add any number every clock cycle. It doesn't have to be 1, it could be 2, it could be 17, it could be 5,483, it doesn't really matter. So long as it's a whole number, so you can express it in some number of bits. And as long as it's smaller than your bit width, or it's within the range of your bit width. So if you had 10 bits, for example, you can represent a maximum of 10,023. You can't say then add 10,024. It won't work. I think he disconnected. Well, I'll maybe give him a second to reconnect. In the meantime, did you guys have any questions for me? Okay, well, I guess we'll just wait here in silence until someone has a question.
Are you just going over what we reviewed in class?
I don't know what you reviewed in class, if I'm being completely honest, but probably.
Okay, just making sure.
Yeah, this is about counters specifically for like your homework problems 1 through 5.
Oh, okay. So is this like the very first problem we're working on right now?
This one, it's just like a general counter overview, but it's the schematic. It's almost the same schematic you're going to be using for all of the problems until you get to the ones that ask you to code stuff up. Because I think every single problem between 1 and 5 is asking about counters. So you just use a counter circuit, and the only thing you're really changing is the bit width. So how many bits you're using to keep track of your count, and also the multiplier here. That's pretty much the only 2 numbers you're changing, but it's the same circuit.
Gotcha.
Any other questions for me?
Can our multiplier ever be like too large?
Yeah, it can definitely be too large because, like I mentioned earlier, say you had a 10-bit counter. You could then add anywhere between 0 and 123. Or sorry, 1,023. that's the ranges of values that this wire can hold. If it's 10 bits, you can't get any higher than all ones, which is 10,023. The issue is, if you try 10,024, you just don't have enough bits to represent that number. You'd need 11 bits, and your wires just don't have that many.
Will we ever get too large if we stick to 2 to the n, like most significant bits? Will it ever give us something that's too large? Like, should we always double check our m value?
You're not going to run into that problem with homework stuff, but in general, yeah, you could. Like, for example, I'm trying to think. Well, actually, yeah, I mean, if you, for some weird reason, wanted to make a faster clock, it's not that it's a weird reason, it's just you can't do it with this configuration to make a faster clock. But if you tried to, say, like double the frequency instead of half it, it's just plainly not possible. If you were to throw numbers into the formula, you'd probably calculate a multiplier that's like quadruple your current bit width allowance. So if it was 1023, your multiplier would probably calculate to be 4,000. But that's only a problem you'd get if you tried to make your resulting frequency, your new frequency, over your old one. So that's the only time you'd really run into that problem. If you're trying to divide the frequency, trying to make it smaller, you're not going to run into that, like, at all. So.
Oh, right. We can't, because the clock out over the clock is always going to be like a fractional number. And if we're multiplying that by our bit width. Okay, that makes sense. Thank you.
Yep. Any other questions for me?
So the clock out over the clock essentially gives us the resistance of the wire, or what? Or no?
Not the resistance. Okay. So there's like a general way to derive this formula I'm about to write, and if you guys want, I can go over the derivation for it, like an intuitive derivation for it. But I'm just gonna write it on the board. So the new frequency you're trying to generate is going to be equal to the input frequency, so the frequency of whatever clock your register is running at. So frequency of the clock divided by 2 to the n plus 1 times your multiplier, where n is just the bit you're selecting. Because remember, this is many, many wires. It's a bus. So you could select the uppermost bit, which is bit n minus 1, or you could select bit, n minus 2 or n minus 3. So instead of picking, if it's a 32-bit bus, instead of picking 31, you could pick 17, 18, you could pick 2, it doesn't really matter. So that's what this n represents here, whichever bit you're selecting. And
so it says n what? N plus 1?
Yeah, n plus 1.
Okay.
Yeah, so I'll go ahead and show a quick derivation of this. Actually, let me... So if this was your clock frequency, and let's just pretend for the moment that we were adding 1 every time, it'll just make the math a little bit easier, so I'll just say that you're adding 1 every time. We can ask ourselves what our bits are behaving like. So say we have count bit 0, count bit 1, count bit 2, etc. And we can say, okay, well, what do these bits look like as we continue, or as we progress? So inside the register, you're going to start with the value 0 if you reset the register. So I'll go ahead and actually write that in. Reset. So if you reset the register, you're starting at 0, and we say, okay, we're going to start counting. At the first clock edge, the bottommost bit is going to go to 1. Because by definition, if you're starting at a number, say, 000, and you add 1 to it, that's going to increment that bottom bit by 1. You're going to go up to the binary representation of 1. So this bit goes high, but the others remain low. And at that next clock edge, the next number we hit is 010. And so count bit 0, this bit goes down. but count bit 1 actually goes up, and count bit 2 remains low. And so we can continue. We can say do the next one. So it'll be 1 1. So this is going to go high at the next clock edge. And this is going to remain high, and this is going to remain low. And then maybe at that last clock edge, both these go low, and the most significant bit goes high. And so we can then analyze kind of the periods of these, or the frequencies. So if we call the period of this, of the clock, TCLK, we can ask ourselves what the period of the clock above it is. So for example, for this one, we have a clock period of this length, which is basically from rising edge to rising edge. But here you'll notice that the period for count 0 is actually 2 of those, 2 full clock cycles. And so this is actually double the period. And if you double the period, that implies that you get half the frequency. So what that means is that when you have your clock and you look at the least significant bit when doing this counting, this is always going to have a half the frequency of the original clock. If you were to then move up to this next one, it's a little bit harder to see because I haven't drawn out the full thing. Let's see. Bit more difficult to see, but this distance here consists of actually 4 clock periods. So we have 1, 2, 3, 4. And so that means that this period is 4 times that, or the frequency is a fourth. In general, you go in powers of 2. So you might have a fourth of the frequency, you might have an eighth of the frequency, or a 16th of the frequency as you go down. So every single bit you go to the next most significant bit and so on, you basically have the frequency again, or you half it again. And so that's why we have this 2 to the power over here. And we have n plus 1 in the numerator, or in the exponent, because in the case where n equals 0, that's bit 0, it's going to be half the period, or sorry, half of the frequency. And so what that means is
So
if you plug, yeah, go ahead.
So our frequency is the clock, and we're just halving it over and over and over again.
Yeah, so every single bit is another half. Yep. So bit 0 is half of it. Bit 1 is half of it twice. Bit 3 is half of it 3 times, and so on. Or sorry, bit 0, bit 1, and 2. So bit 0 is half of it once, half of it twice, half of it 3 times, and so on. And so in general,
Gotcha.
you just take half of it n plus 1 times. Did you have another question about that? Because I see the mic kind of turn on and off.
Oh, sorry. It's just my TV's on downstairs,
Yeah,
so
no worries.
I think it's just picking that up.
Okay.
But so basically, we're just so it also I noticed that it goes more clock edges the higher we go in terms of bits, right?
When you
So
say more clock edges, you mean more like periods, like more time intervals?
yeah.
Yeah.
hmm
Yeah.
Okay. So then, like, what's the significance of that necessarily? Like, what does that
That's-
mean for us?
Well, all that means is, say this period is 1 nanosecond, so this distance in time is 1 nanosecond. That just means our next clock here is 2 nanoseconds. This clock cycle period is 4 nanoseconds. The next one's 8 nanoseconds. The next one's 16 nanoseconds. So that just means in terms of time that our clock signal is getting longer in time, i.e. it takes longer until you get another clock edge. That's all that means. Kind of the
Okay,
opposite
that
of
makes sense.
evolution is frequency. And then
So does that mean
Go
that
ahead.
the response is getting slower the more bits we add?
Yeah, exactly. Yep.
Okay.
And so I did this with the multiplier equal to 1. But in general, if you are adding 1 many, many, many times, well, if you're adding any number a multitude of times, that's the definition of multiplication, because repeatedly adding something is the same thing as multiplying. Say 2 plus 2 plus 2 plus 2 is the same thing as 2, but 4 times. And so that's all this multiplier here is. So if you add 1 a bunch of times, you're just multiplying it by 1. If you add 2 a bunch of times, which is what happened if you put this as 2, you'd be multiplying by 2 because you're adding 2 many times, and so on. And yeah, that's pretty much it. So you can use this formula, and this will actually be helpful for the student who I think left earlier. They can watch the recording later, but this formula you can then use to answer those problems 1 through 5, because most of them ask for, say, the multiplier that you pick, given an input frequency and an output frequency, so the frequency of the clock and the frequency you want to generate, and also given how many bits wide your register is. You can calculate m. You just solve this equation for m. You multiply 2n plus 1 over here, divide the frequency of the clock, plug in the numbers, and you can get m. Once you get m, you round it to a whole number. So if it was 10.15, round it to 10, and then you use that as your m value. And that's about it. Yeah. Any other questions for me? I'm going to go ahead and, are you guys alright if I erase this from the board?
I'm good.
Alright, so no other questions for me? I know I've been hounding you guys all night for questions. It's fine if you don't have any. Alright, well, it's about 6:20, so I think that if you guys, I'll probably stay here a minute or two longer. If you guys don't have any other questions, I think I'll just end office hours early.
You said you record the lectures, or
Yes.
the little office hours.
Yep.
Where do you post them?
Oh, I sent a link in the Discord. Let's see.
Or was it pinned?
Don't think I pinned it. I can though. Let me. All right, I might be able to. Let's see. Jump to this one. Pin. Oh, it's not pinned, but if you go into the Discord and in the search bar you type just the word YouTube, it'll pop up as one of the results where it has my YouTube channel. That's where I upload all the lectures.
Oh,
office hours.
okay. Yeah, I found it. Cool. So then you'll, I'm assuming the, what's it called? It'll take a while before it's uploaded?
This office hour, like tonight's office hours, yeah, it'll probably be like, well, it depends when I get home later. It'll probably be like around 9, my guess is when it's up. But
Okay.
I have posted all of the ones from the previous office hours, except for the ones where there weren't anyone that showed up. But all of the previous
Gotcha.
ones are there as well, and they have like the dates labeled on them. So you can look at those too if you want.
Okay. Thank you so much. I appreciate that.
Yep, no problem.
Have a great day.
You too. Okay, I think I'll go ahead and end office hours early then. I will see you guys tomorrow, same time, 5:30, if you want to show up for office hours. But other than that, thank you guys for coming. Hope you have a good rest of your night.
Thanks, Victor. You have a good night too.
Thank
Very
you.
well.
Good night.
Thank you.
You're welcome. Go ahead and stop the recording too.